Good day, everyone. Today I will be presenting my reinforced concrete beam design using the provisions of the National Structural Code of the Philippines 2015 or NSTP 2015. This project combines both manual structural design calculation and computer aided verifications using Alter S concrete. The objective of this project is to design a safe, economical, and code compliant reinforced concrete beam capable of resisting the applied loads while satisfying the requirements for flexure, shear, and serviceability. By combining manual calculations with engineering software, we are able to verify that our design satisfies the structural requirements specified by the code. This presentation demonstrates the complete design process, beginning with the structural analysis performed during our Module 1 examination, followed by the manual reinforced concrete design completed during Module 2, and finally the verification of the design using Alter S Concrete. For the project overview, before discussing the software output, I would like to first explain how this project was developed. The project was completed in three major stages. The first stage was the structural analysis for Module 1. Second stage was the reinforced concrete beam design performed manually using NSCP 2015 provisions. And finally, the third stage was the verification and detailing of the beam using Alter S concrete. Each stage builds upon the previous one, meaning the software was not used to replace the calculation but rather to verify the and validate the manual design. During Module 1, the primary objective was to determine the internal forces acting on the beam. At this stage, the geometry of the beam and the applied loads were analyzed to determine the reactions, shear force, and bending moments throughout the beam. The calculations included determining the support reactions, constructing the shear force diagram, and constructing the bending moment diagram. These diagrams are very important because reinforced concrete beams are designed based on the maximum internal forces rather than their dimensions. From the structural analysis, the most critical values obtained were the maximum factored bending moment and the maximum factored shear force. For this project, the design values obtained from Module 1 were maximum factored moment, MU equals 250 kilonewton meters, and the maximum factored shear, which is a VU equals 180 kilonewtons. These two values became the primary design loads for the reinforced concrete beam. The two most important values obtained from Module 1 are the maximum bending moment MU and the maximum shear force VU. The bending moment determines the amount of longitudinal reinforcement needed to resist tension, while the shear force determines the required stirrup reinforcement and spacing. These values became the basis for the beam design in Module 2. Using the values obtained from Module 1, the reinforced concrete beam was designed manually following the provisions of NSCP 2015. The process included selecting the beam dimensions, calculating the effective depth, designing the flexural reinforcement, and determining the required stirrup spacing. After completing the manual calculation, the design was checked for compliance with the code requirements. After the manual design was completed, the beam was modeled in Alter S concrete. The software was used to verify the manual calculations, evaluate the reinforcement layout, and to ensure that the beam satisfied the desired requirements. Rather than replacing manual calculations, the software serves as a tool to validate and improve the design. After obtaining the internal forces from Module 1, the next step was to manually design the reinforced concrete beam using the provisions of NSCP 2015. The beam has clear span of 8 meters with a concrete comprehensive strength of 28 MPa and reinforcing steel yield strength of 415 MPa. The design was based on the maximum factored moment of 250 kilonewton meter and the maximum factored shear of 180 kilonewton, which were obtained from the fractional analysis. The first step in the manual design was selecting the beam dimensions. Based on an SCP 2015 section 409.3.1.1, the minimum beam depth for a simply supported beam is the clear span divided by 16. This resulted in a beam depth of 500 millimeters. A beam width of 300 millimeters was then selected, resulting in a beam size of 300 by 300 by 500, which satisfies the recommended width to depth ratio. Next, the effective depth of the beam was determined. This was calculated by subtracting the concrete cover, stirrup diameter, and half of the main reinforcing bar diameter from the total beam depth. The resulting effective depth was 437.5 millimeters, which was used in the flexural and shear design calculations. Using the maximum bending moment of 250 kilonewton meter, the required area of tension reinforcement was calculated. The design was then checked against the minimum and maximum reinforcement requirements specified by NSCP 2015. Finally, standard reinforcing bars were selected to satisfy the requirement steel area while ensuring the beam remained safe and ductile. The final step of the manual design was the shear reinforcement. The concrete shear capacity was calculated first, followed by the requirement shear reinforcement. Based on the calculations, 10 millimeter diameter close-up stirrup were selected with an appropriate spacing that satisfies the maximum spacing requirements of NSCP 2015. After completing these calculations, the beam design was ready for verification using Alter S concrete. After completing the manual design, the beam was modeled in Alter S concrete for verification. The purpose of the software is to check whether the beam satisfies the design requirements of NSCP 2015. It analyzes the beam's geometry, material properties, reinforcement layout, and structural capacity. This allows engineers to confirm the accuracy of their manual calculations and identify any areas that may require improvement. The left side of the output shows the material properties used in the analysis. The concrete compressive strength is 28 MPa, while the reinforcing steel has a yield strength of 415 MPa for the main bars and 270 MPa for the stirrups. At the center of the screen is the beam cross section. The software finalized the beam dimensions as 550 mm wide with 700 mm deep, which differs from the manual dimensions because the software optimized the section based on the applied loads and code requirements. The green bars at the top are the compression reinforcement, the blue bars at the bottom are the tension reinforcement, and the magenta outline represents the closed stirrups. The side reinforcement helps improve crack control and durability, especially for deeper beams. The reinforcement summary shows the numbers, size, and location of the reinforcing bars. The beam uses two number 14 bars at the top, four number 14 bars at the bottom, and four stirrup space at 200 millimeters. The software automatically checks whether these reinforcement details satisfy the design code requirements for strength and serviceability. The software checks whether the beam satisfies the design requirement for flexure, shear, and reinforcement detailing. The software displays a warning status. This does not automatically mean that the beam is unsafe. Instead, it indicates that one or more design checks or detailing should be reviewed by the engineer. Engineering software is designed to be conservative, so warning often serve as a reminder to verify the design before final approval. This highlights the importance of combining software analysis with engineering judgment. This project demonstrates how manual calculations and engineering software work together. And the internal forces obtained from Module 1 were used to manually design the beam in Module 2. Altair S Concrete then verified the beam dimensions, reinforcement, and structural performance. Although the software was produced an optimized beam section, the design process remained based on the same engineering principle and NCP provisions. In conclusion, this project successfully demonstrated the complete reinforced concrete beam design process. Starting from the structural analysis in Module 1, the beam was manually designed in Module 2 following NSCP 2015 and verified using Alter as concrete. This project emphasized the importance of understanding structural behavior, applying code provisions correctly, and using engineering software as a verification tool rather than a replacement for manual calculations. Overall, the project strengthened my understanding of reinforced concrete beam design and the role of structural analysis in ensuring safe and reliable structures. That concludes my presentation. Thank you for your time and attention. I would be happy to answer any questions, but this is an online video, so bye bye.